this makes me headaches.
Yeah.
Here, there. Are we in classical physics, are we in quantum mechanics, then we can predict. Are we in statistical physics, many degrees of freedom, many particles in the system we can also predict. For complex systems, and we can always predict it analytically, right? That's the important thing. Complex systems, we can predict sometimes. If we have systems that are simple enough, we can predict the emerging phenomena, right? That was an important milestone in complex systems. We saw the Nagel-Schreckenberg model, these cars going in one direction, hopping from cell to cell, and we could predict traffic jam there. If things are getting more complicated, like our life, it's a complex system. We cannot yet predict what's going to happen. Maybe it's good like this. I don't know. Question for the philosophers? Yes. So today, next question, why are there no giants? Okay? So by giants, I don't mean this guy, okay? He obviously exists, everybody knows who it is. Nobody?
He's a giant. He was in Game of Thrones.
Yes, exactly. He was the one that kept the evil queen in power for certain times until his brother killed him, right?
Yeah,
both of
he
them.
popped his, the eyes of his opponent, and the brother killed him at the end.
No, together they fell when all the castle.
The last season, it wasn't that good.
When yes, right. Yeah. And the whole castle collapsed, I think he was fighting with his brother, who was also a giant, and then they both fell somewhere. Yes. So I don't mean this guy, right? I mean he's really look his wife. I mean his wife is very small also. That's good. He chose one that makes him feel more superior. And also, I mean, Dwayne Johnson, he's also 2 meters, so he also exists, obviously. So I mean, giants like this, okay? Hollywood had a new King Kong movie. First Godzilla, then King Kong and Godzilla, and the last thing was just Godzilla. Don't remember exactly, but he's 100 meters. Okay, so is this possible? Obviously, it's not possible. Otherwise, it would exist maybe. But why it's not possible? Okay, and that's a question that already our old friend Galileo asked in a very interesting book called "The Two New Sciences." Where he has a lot of stuff, he covers a lot of stuff, and in a very interesting way, by three people discussing with each other. Okay? And what is the argument of these people? It's the following, that if you take a small animal, okay, and let's just take for simplicity the biggest bone in the body, right? It's the femur, and you say it has a length of L, right? So if you have a bigger animal that has a bone that is 3 times, or the animal is 3 times bigger, so also this bone is 3 times bigger, then what's going on with the cross section, right? I mean, that's you see already here. In order to support an animal that has this as the biggest bone, you need just something that is it's not so massive, okay? But when you just take, this is 3 times the length, okay? But in order to support the weight of this big animal, you have to make much stronger bones, right? So this was the argument of Galileo, and he basically says the following. We have a body mass. Should we close the light maybe? Good. So we have body mass of the animal, and this body mass m scales with the function of their size, like m to the power L. M is scaling like L to the power 3. L to the power 3 is volume, right? Simple as this. So if the size doubles, right, so 2m, then you see immediately that you get the animal needs 8 times stronger bones. Okay, this explains this, 8 times stronger bones. So bone strength obviously also scales with L to the power 3, right? It's like the mass. Now, difficult to measure bone strength, right? The good surrogate for bone strength is cross section, right? The stronger bone is thicker, right? So, I have to switch to here. So S scales as the cross section of the bone, right? The R square, which is the cross section. So if the bone radius double, then you have 4 times stronger bones. So if you put everything together, so you say R scales with square root of S, and for S you put the L to the power 3, you end up with L to the power 1.5. Right? L to the power 1.5. So R squared is L to the power 3. So basically, what Galileo concluded in his book is 3 times bigger animals need e to the power 1/2 is 5.2 times stronger bones. Okay? So this was the argument. Doesn't really answer this question, right? If you stop, this question will be answered by one more time. Maybe, I mean, you could deduct from this that the big giant animal would just consist of bones, but we didn't really spell it out. Okay? However, we are 400 years later and we can do some look what there is in nature, right? It's what the biologists used to do, dig in the past, and they make an interesting study. Instead of, let's say here, instead of bone strength, they said it's easier to measure the mass of the skeleton versus the body mass. And obviously, smaller animals, if there's body mass, that's skeleton mass. Skeleton lies in the mankind is stronger. Heavier is stronger. And you see a line scaling, right? But it's all on the line. So for swimming around. If he was on land, he could not exist because his own mass would suffocate him or her. Okay? The general nutrient. So how can we somehow deduct this scaling law? We can say the following. We can say the mass of the skeleton Sm is like its cross section times the length. Right? Cross section times the length. We know from before the mass square and the body mass is scaling like the length. So we can put everything together, and we, of course, remember we want to know the skeleton mass and the body mass. So the skeleton mass and the body mass is basically Sm, where it is like body mass to the power 1.33. Right? 1.33 and baby mass. We get 1.1. This is 1.1. Predict something, you measure it, you have a contradiction between your observation and your prediction. What do? You argue. Okay, so what do you argue? What is the easiest? Hmm? No, even simpler. Your physicists, you're not then they tell you you're stupid.
That's the easy one.
No, you just say, go and try, not just does this and here's one moment. Yes. So weight is not the only factor that affects bone strength. Also, what comes to mind? Yeah, but strength is related to nutrition. Nutrition. And some environment is living and so on.
But this means changing the theory. No.
and probably some functions of other diagrams.
It's just
It's very difficult up to some.
this scaling sign means just what happens when I double one parameter, what happens to the other parameter. Okay? So the easiest is to get the square relationship, then you double the one parameter and you double x to the power 4 for the other one. That's what it means. So you have here the little mousey, okay, that has body mass of 100 grams, okay, and you go to humans that have 100 kilo, okay, and then you have this same scaling relationship to the skeleton, to the mass of the skeleton. That's what it means. It's not an exact situation. Okay? It's exact when you look where does this line cut the axis, right? So it's not interesting. You're interested in good. Same. So this is for length and mammals. Okay? And the same thing happens to the birds. Look, you put all the birds here on this one. So call it in English, but in German it's called Kohlmeiser, if you're interested in it. Well, it's called in German. How is it called in Hebrew? No, Robin is the red one. Robin is the qualification. But this is the Kohlmeiser, I don't know. There are a lot of them, and then you go up until very nicely with our first and almost the same, look at this color. 1.07, this is within the error. Okay? So you can good. Now, coming back to our question, why? Okay? Bingo. Let's keep it simple. Income is 10 times big. Okay, than the regular gorilla. You would be 1,000 times heavier, right? So instead of 160 kilo, you could weigh 160 kilo. Just for mini income, you would already weigh 160 kilo. So what would this mean for these points? Right? We can calculate the points. Right? So the point strength is 10 to the power 1 half. Okay? So 32 times stronger. And there's not much. At least I don't know. But that is anyway, that is giants that would be just gold. dinosaurs. You asked about this. So here the King Kong was 160 pounds, right? And not this one, the small one, the baby King Kong. Dinosaurs. So really reliable data we have from this one. That Noctus. That Noctus from head to tail 26 meters. Right, from here to here. 26. You see that it's how it is built, right? Very skinny, relatively skinny, not like skinny. 60 tons, okay? Much lighter than our baby King Kong, okay? There is some other recent findings on even heavier guy, okay? 37 meters, but not really well proven. That's 90 to 100 tons estimated. If somebody's interested in the relationship between gray matter and white matter. Okay? So, gray matter also there, okay? Dark structure, and the white matter is variable. Unfortunately, the white matter is here black. So to identify the graphically fixed. The gray matter is white. You can add Puma and you see there's support. There is perhaps some scaling relationship here. And indeed, when you I could not have done this now. You take the grain apart and you measure the matter or the volume of gray matter, and you measure the volume of white matter, and you do this systematically for, again, here's little mousy. Okay, here are humans, dolphins, here's the elephant, another whale, in between you have cat and rabbit and the rat and stuff. There's a scaling relationship if your gray matter in the brain grows bigger, evolution, whatever. Also your white matter grows by the same relationship, right? So we have here a scaling of 1.23. How do we get there? Bone strength, but still calculating is hard to get this 1.23. So this we have to consider several parameters. So one is G is the gray matter volume. This is just the volume of this dark pink structure. White matter volume is everything here in between. You see here, I don't know. So we have the particle thickness here. density. How many of these atoms are right matter and the density of and good. So let's do something with the arguments. And here again what it means. So we can say that the gray matter volume is simply S times T. S times T over volume. The number of oxides is the S, okay, which is the surface area, times the density you have here. Okay, the density P times 1/2. Why 1/2? Because we are going one angle from the beginning, right? So this is 1/2. This P, this density, is constant across all one units. Okay? Then you have the W, which is the white matter volume. So everything here, all this fibrous material, and this now goes with the number of exons, right, times L. Simply like this, right? So average length, average number. So you multiply the two, you get the volume of all this white matter inside, and you have the volume G, white matter volume, scales with L to the power 3.
Why is that?
Good point. Why is that? Why the G? The G is this stuff, right? And the L is in the white. So this you have to look empirically into data. White matter volume, and here's the average axon length. You plot them against each other and you get the slope of equals. Okay? So it's called the error margin. Okay? So we get this from the good. Now we can plug everything together. We want to know the relationship between the W and G, right? So we start putting W is here, right? SPL half. Then we can substitute the S. The S we have here is G divided by T, as everybody can see. And then we say, okay, so GT. And then the L we can substitute by just this G to the power 1/3. Okay? So we already have G to the power 4/3, right? Divided by T. Okay? So we have here W scales with, or is proportional to 1/T divided times G to the power 133. But we want to have 1.23, right?
Close enough.
Yeah, but notice this T. How does this scale? We do some more experiment, that's why we show this here. That's okay. And they did a good job. They said, okay, empirically, I find that the thickness to the power 0.4. And then I plug everything together and magically I get G to the power 1.26. So 1.26. Only the last step.
And also
So
the step
the
before that.
step 4.
Step 4.
Also step 4. Resource, but he also doesn't need this, he or she. I mean, what are they doing the whole day? They are eating eucalyptus leaves, very low calories, so they cannot do much actually with their energy. I mean, the energy they get from food. They don't even drink water. Yeah, because then they have to go down. And there they are most vulnerable, right, when they are moving on the ground. So they just get all their water from the eucalyptus leaves, and they sleep most of the time. When they go to the zoo, they always sleep. Very sometimes they wake up to something like this very often the relationship, the scaling between the metabolic rate and the mass. Not of the organism, but it's amazing. This is where it starts. Mitochondria. Mitochondria, mammalian cells. You have here our mousey. All mammals, including humans and cats and whatever. Elephants, this is over 10, 25 orders of magnitude. Where do you get something like this in nature? And everything follows nicely a power law with a slope of 3/4. To come up with this 3/4 is will take half an hour. I don't want to, and it's a little bit boring. So if somebody's interested in this, I can give you the literature. But this was a nature paper. Okay, this was really a big thing. Yeah. So I find this Yes, we have here.
Do you see it?
Yes. Minus.
Just the arrow in the
Shift,
left,
control.
the up left. The up left of this square. Yeah, no, the other side.
Ah,
You can just move this one.
good. So last week when we talked about the requirement of the course and how we get them in place and stuff, I told you that you should prepare over the course of the course a notebook. Okay? In the notebook you write the stuff that you have learned. Okay? And we will go to 4 labs during the semester. We will put data there and we will get some good tasks to analyze the data and we will also put in the book. And then at the end of the semester we have some summary of and this will be 8%, 8 points. And then there will be 20 points on tasks that will give you during the semester that you can choose from these tasks. You can choose the first task was to introduce to us this environment. We have to write a notebook format. This is done here on Colab. Tell us about this. And the next task will be, I think, Google. The next task will be measurement, left of the problem, and particularly
hi, hello. Nice to see you all. Okay, so as Ronnie said, during the course of this course, we will be working in an environment called Google Colab. So if you can see my okay, so when we enter a Google Colab, it's this sign is shown. How do we get in? If you own a Google Gmail account, so there is a Google Drive that is assigned to it, and inside of this Google Drive, one can just press there is add new, and you can choose either add Google Doc or even so already a Google Colab. And the good thing about this because this is an environment that allows us also to write stuff and also to do some Python coding. If you're familiar with Jupyter Notebook, so this is like the same. It works in tabs, just that this is online. It is saved online and you can share it with others. So this is a file shared with Ronnie. How does one do share? You can just press here, and so we give some examples about the basic tool that we will be using during this class. So we were asked to show how does one write inside of this platform. So this works in.
So if you have to work with this. So if you have questions, ask now. Okay.
And everything will be shared with anyone. So just feel free. So we work in sort of tabs. So how does one create a new tab? So you can see the cursor. So it's either adding text or either adding a code.
Always Jonas, it's behind you.
Sorry. So either adding text or either adding code. One can upload the file that you've already worked on or saved. It is saved automatically, so just for you to see. And it allows us to do many more things. If one chooses to use AI while working on stuff, one can use Google's Gemini. And so with that, we will start to see how this looks. So here I wrote some examples about how to write some code. We were asked to either write by our own or using LaTeX writing or the LaTeX format or italic text. So in order to get inside of the tab, one double clicks it. So this is how it is written, and this is how it shows you directly how it's printed. So let's forgive an example. Let's write Licht, so why not? And you see that right away it shows me if I double click it, this tab once again, which means that I'm reassuring that this is what I want to write. So now it is saved. Okay, so this is for choosing. For writing LaTeX, I guess that we are familiar with LaTeX. LaTeX is a kind of
Everybody knows LaTeX?
okay, so just how to implement LaTeX writing within our text tubes here. Once again, I double click, and one can see that if I want just a LaTeX equation or something, it is surrounded with only $2 signs from the beginning and the end. And if I want a LaTeX block, once you double click, one needs to write it within $2 sign. So how to write it here in that. And the great thing is that also provides us to use Python when coding and implementing some graphs plus computations within our notebook. So here, for example, just to reassure and Fatima said from Python stuff that there are some built-in functions using Python, but if you want to use more advanced or some tools that are directed into some certain computing, one can import a certain package that was originally computed to help doing such a stuff. So here, for example, I gave us an example of how to write, how to use such packages, and how to plot the outcome. So here we gave an example. So in order to use some computations and arrays with the numbers, I uploaded the NumPy package, which enables us to easily do line space between get the entire to calculate the entire line and the spacing as how we want it. And also there are some built-in mathematical functions such as NumPy or how to calculate directly sinus and stuff, as we see here. And the matplotlib is how to plot our data. Please make sure that if you want, one can use also after import use the S. So in order not to write the entire name of the package all the time, so one can just use the shortcut. So for your own convenience. So here we show a sine wave, and just make sure that when using getting into our notebook every time, one needs to click the tab in order to call it once again. It's not saved. It is the data is saved, but in order to import once again, every time you get in using because this is an online environment, so one needs to import it once again. So how does one run the Python blocks? So you can see that when I get near the blocks, there is now an arrow which allows me to press it. So one can do this, and this is how it works for us. So this is regarding the example. So just to show how does one add some blocks. So either we could say, let's think that right after this block I wish to add a text. I just clicked on this text, I'll scroll down a little bit just for us to all see. So now we have a new tab. We will call it.
Just scroll up because people don't see it.
Didn't you hear? Sorry.
No, just scroll it up.
Scroll more. Sorry, my bad.
Yeah.
But now I don't see it here. So
Yes.
at the moment, so here. So let's just call our new tab Yoda. Save it and get it in, and we get a new tab. During our class, we will be asked to do some summary of the class, and which will be implemented and written in here. So one can just open code, open a new text tab, double click it, and then write it.
Just want to make a comment. You can also be smart and say, okay, I asked ChatGPT or Gemini to make a summary, but I will see this. Okay, I talk also with ChatGPT, not very good guys. So I notice if what you wrote has a personal touch or is just generated by ChatGPT. So I want you to write it and write what you know. Okay, I don't want to know about ChatGPT again. Last week I was in a selection committee for scholarships, and the students who applied for the scholarship, they had to write motivation letters. But there were students that wrote motivation letters with ChatGPT. I mean, they are supposed to get the scholarship, but you can notice something was written by you or Gemini or Bing or ChatGPT. I will see. Okay? Exciting.
Yes. Yeah, it is set chronologically. So anytime you get in order to use the block, this let's say a block that relies on a block that is written above it. So you have to click first. You have to run the code above it. So it works chronologically. The blocks are set. Here, it's using the Python format. So here we can see this is what we talked about. This is how with one sign of this you can do just the heading, and this is a smaller heading. This is for the points. And when I move down, so we were asked to write. We will be asked to write a small code about the Fourier transform. So here we added a code. We added a text that explains the main thing about the Fourier transform. And one, I'm not sure if you want to know, we have some examples of how to use the Python implementation of Fourier transform.
I mean, we will talk about this more next week, like 2 weeks.
Okay, but could I just show the example that you wrote?
Sometimes it's good for people to clarify. Okay. Go ahead and talk about this again.
Okay, so we will talk. So I will let Ronnie explain Fourier transform for the next class. I will just show how do we implement during this class with using Python. So I provided you 3 examples. One is that a code written by yourself, or one is using just a built-in function using a certain modified package that calculates on its own. So here we have an example. So here we have an example. Here we just more. Okay, so
you need to prepare it, but don't see it. I see it. You visualize it.
So we provided some 3 examples of how to use FFT. The first transform, one can just write on their own an example, but then we can get a result that goes into the result as well. And on the other hand, we have an option. We talked about that we have a built-in function that allows us to already written not only saying Python coding already this Python coding. So one can call direct the answer package with the function that calculates and for that Fourier transform, and you see which much more easily written get the same result. That's here. And just to add some value to it, I also added the possibility to time how much time Bob took in order for if one cares for the efficiency of the time consumed. So that's using the NumPy package of 34/7, and there is another package called SciTime, which gives the same result. Gives the same result, and this time it was just 28.
What is this?
I think it's meant. Yeah. So SciTime was a little bit better. And for this, all will be shared with anyone who wishes to. We have also example about the bench that we were asked to do. So also there are one can do it now. So this answer also will be here. We want to for this example one there is a download a certain file that contains data that works. So it's not that on good, so this is why you get an error, because here the final concept that be shared.
I would prefer to have everything organized under, and one topic lecture notes, and one topic scripts. So this would be I don't force you. You decide by yourself. But it's not next. Is EEG, and left is so you can solve it, but only well, yeah, so you have to people didn't. And tasks. So you see, tasks are here. Here are the tasks. This was one of the reasons of you to come to get.
Better than last time.
Ah, you were okay last time. Just all the time excuse. Which was not necessary. So No, there are some presentations here. These are the tasks. And the next one is the EEG analysis, then it's the script pass filter. So these are all tasks. You can choose whatever you want. If you don't do any tasks, then and your notebook is perfect, you get 80 only. Okay? If you want to have 100, you have to go more. You have to have a perfect notebook and to do at least two you can just look. You can just get 20 points by being all the time the volunteer for whom you report the data. So here, the one that volunteers to get the EEG recorded gets 5 points. The one that volunteers in the virtual reality environment gets 5 points. So you get 20 points just by being the volunteer. Hmm? Yes, yes. And then he said,
I found it.
Wow.
Right in my backyard.
When was this? In the 1800s?
I think, yeah, something like that. So the giants exist. It reminded, when I saw the title, it reminded me.
I didn't notice. I have to do this, I have to read about it and put it also in the lecture. Yeah, thanks for your summary. I think that was good.
It is an introduction, I guess. But,
no, but it's good for people who are not familiar with the collab, you know, start going.
So you just publish it, and there are many internet guidance.
Yeah.
So
Yeah, it's,
that's why I didn't upload the file, because I thought everyone just would be themselves on their own.
yeah, but I will put it in Lambda, and then everything is organized. But we don't need GitHub. It's not,
And I think there is no need.
no, it's just complicated things.
There are many types of animals which I was not familiar with.
I also most of them.
Right?
I mean, fox I know, and sheep, but
What? I
I have no idea what is
Alright, I'm not sure.
tufted ear marmoset. Idea. Pygmy lemur are these monkeys that live in Madagascar. Striped tail, you know.
I know lemur because I live next to the safari, and last year a lemur ran away.
Ah, yeah.
So I joined them in searching for it.
I always wanted to live next to the safari, next to the park. It's
Yeah,
nice there.
so he escaped to the park. So,
Yeah, of course.
So we just went to sleep for
They are shooting it with.
No, for him, just because it's lemur and it's
What
not
came
dangerous.
back?
No, they were looking for it for hours.
Yeah.
It was, I think, he ran away in the evening, and they only found him in the park around 5 a.m. So the keepers that knows just waited for him under the tree, and about 6 a.m. he woke up, he just got down back to them, and they walked together. But he wasn't in the tree next to the safari. He went like for 1 kilometer.
Little bit exploring.
Yeah, he went for 1 kilometer, just found the tree. And went to
Yeah. Yeah, I walked once with some monkeys that are called cake monkeys.
Okay.
And they, these are the monkeys with a tail. Basically, they are from Algeria. And
There is something Algerian written here. Algerian. I saw it. Algerian hedgehog. No, Algerian hedgehog.
Ah, yeah, no, that's not.
Yeah.
So so in Germany they have a hill where they live freely. It's 20 hectares, I think, and there are these and it's tourist attraction. You know? The tourists go there and sometimes these monkeys come back, and then this they go to every village, and they are looking at the house. Shopping, you know, it's cool. You know, they take our bags and then they take out whatever they want and
Are we talking about real monkeys or are we
No, real
being
monkeys.
racist about?
No.
Okay.
No,
Just
real-
one.
No, real monkeys.
They come to your grandmother from
Yeah.
there.
It's real monkeys. And I was there when they walked. I mean, I came too late, but it was very interesting. The monkey was took one of the yogurts, you know, and then it didn't know. It noticed. I mean, there was a nice picture. That tasty inside. It didn't know how to can,
Get it off.
we know how to open, but and then it was looking and squeezed out the yogurt. So that's complicated. Taking the scaling factor times this function, and lambda is a positive number, and learn that solve this equation right to the power g of x is like x power. So c so f x mathematics behind it. So, shortly, what is the power law? The power law is kind of distribution. So you have constant times x to the power minus alpha. Kind of a demonstration constant, y is infinity, and c, like this in integral, you get alpha minus 1 divided by x min to the power 1 minus alpha. So this already tells you something about alpha, right? Alpha is 0 or smaller than 0, then, or smaller than 1 even, then you cannot formalize it, but the probability distribution function. So alpha has to be above 1, right? First thing we know. Okay, this example alpha is equal to 1. This actually is not really a power law. You can get it. I mean, empirically you can get it, but it's not strictly a power law in the mathematical sense. So here's the examples. Practically, they're all in black. So what is what? I mean, what is one, this one, or this one. It's a log plot. So we plot over log p over log x. Notice which one has an exponent of 1. The upper or the lower one? The upper, right? Because it's a slower decay. So the higher your alpha is, you can see here, the faster the decay, right? So this is 1, this is 2, this is 3. So higher alpha, faster decay. Now we know a lot about exponential distributions, right? We talk about this a lot in physics. So what is the difference now between the power law and an exponential? So here I have a comparison. Again, the straight lines, it's a log-log plot. So therefore, when it's a log-log plot, and you get a straight line, it's power law. When you get something like this, it's an exponential, right? Then when it's an exponential, a linear line, how would you need to plot it? When you get a linear line, you get a log-lin plot, right? Log-lin, you get a straight line from exponential. So this is log-log plot, and what you see here is so events that are impossible for an exponential distribution, so everything that is passed here is impossible for such an exponential distribution, right? Alpha distribution of 1. But such events that are unlikely for an exponential are likely for order. And order has this long tail. It also covers two events. And because here, so what is the example? Now is right? And what is Gaussian distributed? Yeah, if you go to the university and you record the height distribution, then you get the Gaussian distribution, right? So you have the few students that are smaller than the average, and you have few students that are but the majority is in this margin 1.7, 1.8 meters, and you get a balanced curve, right? So very unlikely to get extreme events. Very unlikely to get extreme giant student for a London university. But if it was power distributed, we had giants walking around in the university. Can you imagine? But luckily, it's not like this. Okay. So that's the difference between power law and exponential. Examples. A lot of examples in nature about power laws. Okay. And there is some reason for this. Right? You asked this before. But let's look at some examples. Family names. Okay. You have. So how was this? You have a lot of people with a single family name, and you have a lot of people with different names. So I think it was like this. So this would be basically the Coens. Okay, we had this already. I every time forget. These are actually the Coens, and this is what is an exotic family name? I mean, many exotic family names. You have only a few people that have this exotic family name. Where does this not work? Where don't? Which part of the world do not get power like this? China. Why? Because in China you have only 3 family names: San, Ma, and most of the people have the same family name, right? In China. More than we have people in documentary that in Beijing they were looking for Kang Liu. And there were 10,000 Kang Lius in Beijing, you know? So, go figure. I think it's, I mean, it's, China is special. Yes? So the y-axis is how many, this is normalized actually, so, but you can imagine it like this when you do an experiment and you, in the example of the height of the students in Taiwan, you have one it says 1 meter 70, the other one says 1 meter 80, 1 meter 60. Then you have the area of data, and now you start sorting. Okay, how many of the students have 150? Okay, so many. How many? I mean, this, if it was a comma, okay, it's exponential, but you, and then you go to the next. How many students have 160? Okay, it's less. How many students have 170? How many students have 2 meters? You know? So it's just like this. And here you do the same. You ask people, what is your family name? Okay? And then you end up that most of your people say Cohen. Okay, this is here. But how can I get this one? So maybe it's the opposite. That these are the coins and these are the.
Within a group of, let's say, 10,000 or 1 million people, the probability that they will always be coins or probability drops. But still, feel right.
But forget about this, okay? Forget about this. I'm more comfortable to talk about this. Well, go and ask people how much money they have in their pocket. The most people say, I don't have no money, like me, okay? Then you get somebody who's called Elon Musk, and he also doesn't have a lot of money in his pocket. He says sometimes he's sleeping in a friend's place because he doesn't have cash money to pay for the hotel, right? But on the paper, right, he said something like this. He says a lot of stuff. So anyway, he's watching on YouTube, so I have to be careful. So these are the Elon Musks, okay? It's very rich, but low probability to find this guy in Bailan. Okay, in Bailan you find the poor people. No, stuff. But you get the point, right? Citation. You have a comment? You're one of these. You want to say something? Ah, okay.
I just understood.
Okay. Citations. You have a lot of papers that are not cited so much, and your few papers are cited a lot, right? This is Imri. This is your specialty. Sun flares. Okay. You have a lot of small events on the sun, and you have a few big events. Okay, it's also self-organized chemical. Earthquakes, a lot of small events, a few big events, and religions. These are also understand. So there's only one religion.
A lot.
I think these are the. No, then this should be here again. So next time I take out the surnames and the religions because I cannot understand. I think. Exotic religions. Exotic religions.
That's huge. Yeah. It's billion.
Yeah, that doesn't make sense, right? Okay, I have to look at. I thought I understood it, but I forgot now. I have to look at this paper. Good. Then we, in statistical physics, we all the time derive moments, right? In order to describe a probability, distribution function, the most important thing is to calculate its moments. What are the moments? First moment is mean. Second moment is variance, right? Proportional to variance. Third moment is somehow how symmetric it is, right? Not stiffness, I forgot the name. Skewness. Okay, skewness. How it is skewed. Is it symmetric? For example, Gaussian has that's equal to 0 because it's symmetric, right? But if you have something that is not symmetric, you get a third moment that is not equal to 0. How do you calculate it? Simply you plug in x to the power k for the kth moment times px. You do the integral. You can do this easily by putting in here the power law, c to the power minus alpha. Actually, c we know already, we calculated it before. You end up with this expression. And of course, it goes from x min to infinity, or from 0 to infinity. And you see already that you have here a problem, right? So this explodes. You cannot integrate it. Okay? If alpha is not greater than k plus 1, right? So you need to have something that is a negative exponent. If it's positive exponent, you cannot integrate it.
No. So if I have something with, we said that the minimum alpha can be 1, right? So
no, it has to be greater than 1.
Right. So can I calculate the variance of stuff that have alpha?
No, you cannot. Okay? If you have something, so we know alpha has to be above 1, but if you have an alpha that is between 1 and 2, you have a moment. So it doesn't make sense to ask the question, if you have a wealth, what is the average wealth? Statistically, it doesn't make sense to put forwards. So there is, I mean, we can calculate it, but it doesn't exist. I mean, it exists in the calculation because there's a difference between the average calculation data, moment, and the moment that exists in the distribution. But for alpha between 1 and 2, there's no moment exists, right? If you have something between 2 and 3, then you have the mean, but no variance. And if you are above 3, between 3 and 4, then of course you have also the variance. But what's the problem with something, a power law that is bigger than 3?
Decays very fast.
Decays very fast. And what was the special thing on the power law? You have a long tail, right? You have a very big difference between exponential and power law. If it decays very fast, it's almost like an exponential, right? So everything that is above 3, if somebody comes and reports to me, I found the power law with an exponent equal to 5, I say, okay, good, but not so amazing, right? And really the power laws that we looked at before, they were the interesting ones, right? They were L to the power 1.5. Or we had here in the brain 1.23. So there are really some interesting stuff that falls into this category between 1 and 3. So in general, you can write the moment exists. In general, for alpha is larger than k plus 1. And how do you calculate it? Plugging in the alpha and the k, and then you get your moment. Okay.
So for us, it's irrelevant to calculate moments because we're talking about interest.
Yeah, if you talk about power laws, it's important to know. But I won't give you an exercise. Calculate the first moment of this power law where the exponent is 1.5. It doesn't exist. Ridiculous, right? So here this is exactly the difference I wanted to talk about between a sample mean and the statistical mean, the statistical moment. So if you take data and put it into MATLAB, you can always calculate the mean and the standard deviation, right? But the important thing is now, if you generate power law distributed data, okay, then you can do this easily. You can just do this in NumPy. You say, I want to have power law distributed random data with a exponent 1.7, where we know mean doesn't exist and variance also doesn't exist. So now what happens, of course you can calculate the mean and the variance, but what happens is, look, so when you take larger and larger sample sizes, then you get all the time a different mean, okay? So larger sample size, so you start with 100 data, you get some mean, then you repeat it for sample size of 1000, you get different mean, and so on. So you don't end up with the same mean, right? Also, you use the same distribution. The same with the variance. You know, you don't converge towards the mean. I mean, you don't get the same mean, basically. That's because it doesn't exist.
That's
So-
perhaps because the probability one even gets the more extreme rare events when adding up more samples.
Exactly, that's the point. Because when you look, when you go to here, you simulate this distribution, for example, right? And you sample this distribution with 10 points. Okay, the likelihood that you get something from the end of the tail is very low. You will sample here, okay, randomly. So your mean will be very small, right? Now you have 1000 data, so the likelihood that you catch one of these big fish here is higher. And then your mean also will increase. And the more data you sample from this distribution, the more often you will hit the tail, and this will increase your mean or your standard deviation. So that's the point. So, yeah, so both diverge when you take something 2.05. Now we have you see here, it also converges towards the mean. On the sample size, but we know that there's no variance, so the variance is diverging. And if you have 3.01, you see that both are converging. Okay, so if a moment doesn't exist, it's infinite, the sample estimate grows with the sample size. That's basically the message. Another thing, also we already covered this in the beginning actually. For the power law, you have a very interesting property. So you compare the PDF of a power law at P of x and the shifted version. You take the definition of the power law, C times x to the power minus alpha, and then it's basically very easy to rescale the power law, right? You just can shift it up and down. That's and you rescale it by this constant c to the power minus alpha. This you can only do with power laws. No other function do this nice rescaling, right? From where do we know this rescaling? From statistical physics. So what is related? You can take these domains, okay, small domains of is when you get two power laws that have the same exponent, they are the same. You know, I mean, if the one is, they will be parallel, right? Because they have the same slope, the same exponent. So you can just multiply by c to the power minus alpha and collapse the number. This you can only do with power laws. By this, that they have a power law because they collapse the data on top of each other, right? So a tip to when you plot power laws, how to do it? Not like this, okay? Always on a log-log plot, because you want to have a straight line that you can fix. That's not a good example, right? They took always the same bin size, right? And when you go to larger scales, then your bins have many more points than they have here in the beginning. So you want to have a logarithmic bin, right? That is large at the beginning, small at the end. Somebody else says, no, here you have some event, so this is the fit. Doesn't happen here, okay? When you bin it properly with logarithmic bins, you get a nice, more or less straight line, okay?
So what is the binning in the middle?
This is a linear binning.
This is linear binning?
Yes.
This one.
Yeah, so you take always a binning of 10, for example. So a binning of 10, no, this is maybe a binning, no, the scale is long. Distance between the points, right? The distance smaller and smaller. If you look equidistant on a linear scale, you have many more points here, and that's why you get this balagan. You always use and logarithmic bins. There's a function in NumPy that calculates you logarithmic bins also. You also talk about if somebody has questions about it. So let's talk a couple of. Let's start perhaps with the origins of scaling or power laws. And in physics, we have different. One, you know from statistical physics and thermodynamics, it's when you go to a phase transition. Okay, when that's criticality. Criticality, you get the power law. Self-organized criticality we talked about last time. I have another slide today we can discuss again. Then processes that are multiplicative. Differential attachment, differential processes also generate power laws. We have sample space reduction processes. When you are at PC in mathematics, At TC, at critical temperature, the spins not only act locally, but they cluster. Okay, you have emerging aligned spins, and you have the local correlation matrix. Entire system, and when you write it down, in magnetism you get for the susceptibility, the whole susceptible to magnetic field, that goes like 2 minus Pc divided by Pc, up to the exponent minus gamma. That, and this is obviously power law, right? And my critical exponent gamma here, this gamma is critical exponent, also very important. And the interesting thing now is that materials with the same critical exponent, they belong to what we call the solid. Okay? So it means that in physics, different materials same critical exponents, as a critical point, they are identical from physics. So it also means that if you find a model, sort of a critical exponent, that the model exactly represents the physics. Doesn't happen so often, but sometimes it happens. Okay? So very compare magnetic properties to percolation. Recognizability, what are self-organized systems, SC systems, they are driven out of the electron, so they show critical behavior, meaning that the functions of absorbing quantities of power moment. As you see, systems are not normally time-tuned, they go with the critical point, not like when they are want to reverse without so the time to which we can do that intuitively. So often intuitively complicated to understand.
They started equilibrium and then
never at equilibrium.
so what out of equilibrium means that they never get equilibrium, always focusing near the.
They're always. This was the example we had with sandpile, right? So you dance on the sand grains fall and you build this but you can model this simply. Look, you have your sand small, so to say, and then you put your top some sand, so to say, and then you go into the next level. All of them in the lower level are already you put only a bit, you know, and trigger a big avalanche. So this is how you model it. Another example is earthquake statistics, self-organized cryptography. You have here straight line in log A, you have its exponential distribution. And here you get the exponent of 1.3, 1.5, so this is the power law. And here you get, yeah, but practically, when I ask you how long, what is the average duration you are in deep sleep? Yeah, it's 12 minutes. So the average duration tonight is 12 minutes. After 12 minutes, you either have a short arousal, so you destroy your deep sleep, or you have a transition into light sleep. Okay, or into REM sleep, not usually, but so. But in one piece, you are in deep sleep, in average 12 minutes. Okay, or 10 minutes in REM sleep. Okay? So it's not. Yeah, for babies. Also, this is for young people. Okay, when you short, so you have a lot of it's self-organized because you can say this awakenings, these short arousals, they are like avalanches. So you have a lot of small awakenings, so small avalanches, and a lot of big avalanches. This is basically your neuronal avalanches in the brain. So this is why it's not asking the same questions like the reviewers who rejected my crown. No, it's good, it's good. It's important questions, right? So another thing is when you multiply, just by multiplying random numbers, you get a power law, or actually a normal distribution, but if you do some constraints, you get a power law, as you see here. Interesting. The preferential processes. This is basically the rich gets richer effect. Okay, so we will talk about this when we learn about networks. That for growing networks, you preferentially attach to the more connected nodes. Right, so we will talk about this in networks, but also gives you power laws. And maybe the last example for today is the sample space reducing process. Very interesting. So what is it? It's basically that a process in which the future outcomes depend on the history of the past. What is an example of this? Life. Okay? When you are a baby, you have all the options. You can become a composer, a politician, a big rabbi, or a physicist, an actor, a soccer player, anything you want. The more life develops, you reduce your sample space. Okay? So, a 65 years old professor in the physics department cannot become anymore a soccer player at Real Madrid. Not even I, but I'm not 65 yet. But even for me, this sample space is already finished. Okay? Yes, so this is an example of a sample space reducing process. It's an out of equilibrium process, and so we have the directed networks process. So this is how Google and fragmentation process is a sample space reducing process. Or when you break spaghetti, how do you break spaghetti?
thing that you spin.
Yes, if I ask this immediately, it would shoot. But there was an MIT study that explains that when you break the spaghetti like this, little pieces lying around. What do you do with this thing? You reduce the sample space, right? You reduce the sample space, and then you break them. You get them into two pieces. You can try the total, and you can read it. There's taxpayer money used at MIT to make a really thorough experiment on this. So, yeah. Another example is just some toy model. You start with a UBR, with a cube of 13 sides, okay, 13 numbers, and then you throw it, and when it shows up number 9, for example, then you exclude everything that is above 9. Okay, and then you throw it again. So this way you reduce your sample process by making your die smaller and smaller until it's only a coin basically. Right? So it's a sample space reducing process. If you do this many times, you get what is called the Zipf's law, which is smaller with the exponent -1 into the power. Exercise in the computational physics class. Yeah, you can do this at home, and you can know how this exponent -1. Good. Let's make a break here, and next time we talk about calculation and factors. Good. Thank you very much, and see you next week. Shabbat shalom.
So we have to talk about the basics or just the brief what is it talk about?
No, it's more on the practical side. Yeah. The physics, I don't think it's so. I mean, if you're interested, we can also talk about physics, but it doesn't really help us much. So I want to be a bit more practical. Your tools that you can later use in your research, your analysis. Really understand